This is to update you on the package that you hopefully will receive on Monday, even perhaps today, Friday. You will receive 25 sets of these things in a plastic container, 25 of those, and 25 sets of 6 little samples of elements, like so. So that comprises the class set. You can get the students to put the elements on the sheet, and you will see that the thing that these have in common is that they are all found on the periodic table. They're all pure, all the atoms are the same within the one sample. These are all sulfur atoms, these are all carbon atoms, these are all lead atoms, and so on. Whereas the table, or you or me, the atoms in us, or the table, are all mixed up. There's carbon, hydrogen, oxygen, and so on. So they're not elements, so they won't be found on the periodic table. Air is another example. It's a mixture of nitrogen and oxygen and argon. It's not on the periodic table. It's not an element. The same with water. Is H2O. It's got hydrogen and oxygen atoms in it, 2 kinds of atoms. It's a compound. It's not an element. You won't find water on the periodic table. The old meaning of the word element, the metaphysical meaning, included air, water, fire and earth. But in fact they're not elements in the scientific sense. Earth, dirt, is made up of a heap of different sorts of atoms. Silicon, oxygen, iron, all sorts of things. Air, we know, water we know, they're not elements, they've got mixtures of atoms. But what's really distinctive about these things is they're just one kind of atom in each of them. The second thing in common these have got is that we've got the same number of atoms in each sample. So they're all kind of the same size. Some of them are bigger than others. The lead's a bit bigger. The copper seems to be one of the smallest, and so does the carbon. But they've all got the same number of atoms. What this means is that when we feel their weight, the difference in the weight of the sample reflects the difference in the weight of the individual atoms. So when they feel the weight of the lead, it's noticeably heavier than, say, the sulfur. So that means the lead atoms individually must be heavier than the sulfur atoms, because the same number of atoms in each sample. So it's a fair test. That number is actually a very big number, of course. You wouldn't be able to count it. It would take hundreds of billions of years to count the atoms in each of these samples. It corresponds to 100 billion trillion atoms. So that's pretty cool to know how many there are in each of these. The kids will probably find that cool. The first thing that they'll see on their sheet, on their activity sheet, is all of these listed in order of alphabetical order. So first is aluminium, B, C, carbon is the next one, copper, sulfur, I think, S, lead, then sulfur, then tin. So that's just a linguistic way of putting them in an order. But what we're going to do in this experiment is try to work out the order based on their weight, the lightest to the heaviest. With the lightest we're going to put on the left-hand side, which is the right-hand side, the way you're seeing it on the screen. But from the kids' point of view, this is the left. And if they just pick up and feel them, they will clearly feel, one after the other, oh wow, that's the heaviest one. And this is clearly the lightest one, carbon. So they can put the heaviest one on the right, the lightest one on the left, and then they can sort of juggle these ones. Tin is clearly heavier than all of these other ones here, so it goes just before lead. And eventually they'll get a fairly common, most of them will get that sequence, except for sulfur and aluminium, because they're pretty close to each other in their weights. Aluminium is number 13, sulfur is number 16 on the periodic table. That's their atomic numbers. And so they feel much the same. So they might get that wrong. So I'm going to put that in the wrong sequence. Sulfur first, then aluminium. And that's okay. We're not trying to they're not trying to win a competition in this, they're just trying to make a reasonable guess as to the right sequence. So the next stage is to clarify or confirm with more accuracy whether this is the right sequence. Now they can do that with a mass balance, like actually weigh the number of grams of each of those, or they can also do it with a beam balance, which is what we've made here. And this is one of the earliest kinds of ways of measuring masses in science. It consists of 3 bits here. We've got the base with a hole in it. We've got the post, which goes here, and there's a little metal screw coming out. And this is the shaft, the aluminium shaft, aluminium beam, and 2 shafts coming down. So we just put the screw through the hole, and this has been pretty well balanced so that they're equalised. There's an equal weight on both sides. So they can just bring those around to the front, like so. These can spin around. That's okay, that doesn't make any difference to the results. So what they now need to do is use this to confirm the right sequence. If they just take the 2 end ones, the heaviest and the lightest, it's really clear. That goes right down to the table. So the lead is clearly heavier than the carbon. But we're more interested in comparing the ones that are next to each other to try and work out the relative weights of the neighbours here. So we're going to pick up and compare carbon and sulphur first, or whatever they've chosen. So we put the carbon on one side. Actually, it might be better if we held the shaft so that that's stabilised, and we put the sulphur on the other. And when we let go, we can clearly see that the sulphur is heavier than the carbon. So that confirms that they got it right, that putting the carbon there and the sulphur there is good. Okay, the next pair would be sulphur and aluminium. This is the 2, remember I said, were pretty close in weight to each other. So we'll just hold the shaft there, put the sulphur, put the aluminium there, and see which one is heavier. The sulphur is heavier than the aluminium, not the other way around. So now they can correct their answer. Sometimes if they're real unsure, they can switch these over to the other side, because these mass balances are not always perfect. I may not have balanced them exactly right, but they should get, you can see that here it's also going down on the right hand side, so that sulphur is heavier. We've changed this around now. Now we've got carbon, aluminium, sulphur. Now we compare sulphur and copper, and there's a clear winner here. All the others are as expected now. Copper is way heavier than the sulphur. Copper and tin. I find these really pretty elements actually. The colours are just really nice. And you can see that we've got that right. Tin is heavier than lead. And finally, tin and lead. If we bring those 2 over here, then we see that lead wins out. Lead's heavier. It might also be worth pointing out that of the 6 elements, 2 of them are non-metals, and they're on the right-hand side of the grey diagonal on the periodic table. The point of this particular experiment is to show that the sequence of the weights also matches the sequence of their atomic numbers. The lowest table on the activity sheet is to rewrite these elements in order, the correct order of weight, and then to write below their name and their symbol their atomic number, which they would need their periodic table for. So they'd look up carbon and see its atomic number 6. That's a pretty low atomic number, and that's not surprising because it's the lightest of these 6. The next one is aluminium. On the periodic table, its atomic number is 13, a bigger atomic number. It's heavier. Then the 16, heavier again. number 30 for copper, heavier again, 50 for tin, and the heaviest, the atomic number of lead, is 82. If we had tested all 92 elements that we find in the world, we could actually create our own periodic table, starting with the lightest one, hydrogen, going right through to the heaviest one, uranium. Uranium, if we had the right number of atoms, the same number of atoms of uranium, of course, it would win out against all of the other ones, and so on. The thing that mucks up that experiment is that some of them are gases, and some of them are liquids and solids, so that makes the measuring of their weights a little bit trickier. Nevertheless, this is a great way of showing how, in a way, they've created their own mini periodic table with these 6 elements, lightest to heaviest.